AIgean is pronounced much like the sea and archipelago around the Mediterranean. And yeah, as you mentioned, it is an ML framework on top of our Galapagos framework. So a lot of what maybe some people may not be interested in the ML side of things, but might be interested in the Galapagos framework. And for those, you can see this as a case study of what you might want to do if you want to bring in your own application layer. All right, so machine learning, it is a very popular topic of research. It's used in many areas, many applications, from medical, finance, biology, safety, pretty much everywhere. And because of that, it's also been highly researched within the computing community as well. This wide usage in the world pushes the limits of many of these devices, and we push many metrics. So some metrics include performance, some other include energy, some is performance per watt, which is a very popular one, especially within the FPGA community. And this is leading many of our researchers to consider heterogeneity. Oh, sorry, let me just change my mouse scroll. There you go. Okay, cool. So here's just an example of where you might see this sort of machine learning heterogeneity, all the way from the edge device, if some of you have an iPhone, but it's in most phones anyway. And the iPhone particularly, it has these neural engine cores. So these are heterogeneous cores specific for machine learning. So that's on one end of the spectrum. We have it on like these edge phones here. I have one right here. Can't really see it because of the blur. And on the other side, we have it in large multi-node data centers. So instead of a small edge device like a phone, you have it in a dedicated, maybe even power-hungry accelerator. We can think of GPUs as some of them, but there are also whole startups dedicated to making these AI chips. So you can see that we have machine learning heterogeneity on all ends of the spectrum when you talk about kinds of devices, or if you think about a cloud from the edge all the way to the data center. So this introduces a really big design space. So like I mentioned, there's many kinds of devices from phones to data centers, but even within there, there's all sorts of topologies. So how are all these things connected? Are they connected over the internet? Is the data center, do you have your own communication protocol within there? So that's another design space to play around with. There are also differing constraints. So you can imagine that your phone and a backend data center would have very different constraints. I may not want to chug out the most performance out of my phone, but I really want to make sure that my phone doesn't heat up in my pocket. Whereas a data center, I might be a bit more liberal with these kind of things. And there's all sorts of different algorithms. So you can think of a machine learning expert who doesn't really know or understand or even care about what device these things are running, but they just want to get the best algorithm, the best accuracy for their application. So they would be maybe within the physics community, for example, like the people that we're working with, or maybe in the biology environment, where they just said, hey, I have my data set, I want to get good accuracy. You run it somewhere and it'll magically come up with a result. So we want to make a framework where you can tinker with any of the above without affecting the rest. So I alluded to the machine learning expert who doesn't want to care about the stuff below, but maybe there could be someone who works in the data center and is saying that I'm not an expert in machine learning, but I know that's a big application. I want to be able to take that kind of realistic application, and I want to work on different kinds of communication protocols. And I want to be able to just rip that application, bring it to my area of expertise, change around the communication protocols, and still have it work. So you can see that there's all sorts of things to tinker around with, and I'll get into more of those details in a bit. So I hope that briefly motivated some of what we're going to talk about, but just a big overall outline. I'm going to talk about a bit more of these machine learning frameworks, and I'll categorize my own abstraction layer within the machine learning stack. I'll go over AIgean, which is a combination of two different frameworks, HLS4ML and Galapagos, and a case study in exploring the design space and with some results at the very end. All right, so a few machine learning frameworks here. I'm guessing a lot of people in the audience have probably seen some variation of an ML framework. So here's TensorFlow, here's PyTorch, there's many more, Intel DLA, Xilinx XFDNN. And you may ask, what do these different frameworks offer? not only do these different frameworks offer different things, but I would also say that it depends on who you ask. So an ML expert would say that this is a way for me to get to deploy ML algorithms. Maybe someone else might say that this is a large matrix multiply machine, and I want to do many matrix multiplies. So it really depends on who you ask. And so there's already that bit of variability, and I want to lead into this ML stack that we have here. So at the very top of the ML stack that we've defined is the application and algorithms. And again, this is probably where that ML expert would sit. So this is where they would define what layers they want, what kind of quantization mechanisms that they have, compression pruning, mostly at the network level. And how that's going to happen, I don't care, nor do I want to see it at this level. But below that, you can imagine that there are physical connections. So now we have our neural net and we want to deploy it on a heterogeneous environment. So, and how is this heterogeneous environment connected? So are these different nodes that are running different parts of my network, are they connected via TCP, UDP, PCIe? These are all things that we would worry about at this level. And at the very bottom, we have the specific hardware itself. So you can imagine that maybe for a GPU, I don't have that kind of flexibility, what I want my individual hardware nodes to look like. But in an FPGA sense, because we do have that kind of flexibility, we even have room to tinker at this level. So with our framework, we can tinker at the very top because we have those abstraction layers. Galapagos also gives the abstraction to target many different cluster deployments. And at the very bottom, because we're using FPGAs, we can also change the hardware. So you can imagine that there's a huge design space that you can target with our combined framework here. So we also, and I've alluded to this quite a few times, but yeah, we want to allow researchers to pick and choose what they want, what they care about. And we also want these layers. So I've kind of alluded to the fact that maybe someone might want to care about a specific layer, but within a really large research group, you might notice that maybe I can, for example, I'm an ML expert, but I want to dip my toe in cluster deployment. So I want to be able to partition my network across multiple devices and choose a communication protocol that makes a lot of sense for my particular application. And having all of these things as open abstraction layers allows us to blur these lines and make these modifications. So that's another thing that we want to push for. We don't want to just restrict you to certain APIs at different levels, but we want everything to be open and for these things to flow, because at the end of the day, we're a research group here. So here's a brief overview of AIgean. So it's pronounced much like the archipelago in the sea. So there's the actual AIgean is spelled AEGEAN, and we thought we were a little cheeky with subbing the E for an I for AI. It combines two existing frameworks. So one framework being HLS4ML, which generates HLS synthesizable C++ IP cores for with a machine learning target, as well as Galapagos. And Galapagos takes a bunch of hardware IP cores, deploys it across multiple FPGAs, connects it together, and gives the user a connected cluster. I'll get into a bit more of detail right now. So HLS4ML, it's an open source project, and a lot of the people working on HLS4ML are my co-authors on this paper. So before we kind of joined the project, for an input, it would take just the description of the FPGA resources, and it would be for one particular FPGA. So I would say that my FPGA is maybe a tiny Zinc board, and I would give it a description of the nets that I want to run, and it would probably time multiplex quite a bit with a lot of looping to make sure that it fits on my large edge device. But I could also say that I have a huge Alveo card. You can spatially lay out your whole computation across this Alveo card. So yeah, that would be a different output. So the output is HLS synthesizable C++ code that can fit within the constraints that you specify. So before we joined, this was within one device, but you can imagine that, if you have a framework that can make one FPGA kind of look like, or make multiple FPGAs kind of look like one FPGA, then we can take this a bit further and extend this framework to multi-FPGA. So that kind of leads to the other framework. So this is a framework that we've worked here at University of Toronto with myself and many colleagues. So this is Galapagos, and what it allows a user to do is a user would describe a cluster of streaming IP cores. So in our land, we're using Xilinx, so it's Xilinx Axis Stream, but I'm sure you could port this over to the Intel world as well. So we have a bunch of streaming IP cores that are all connected with one another. And as you see, what's inside the red box, there isn't specifically any notion of what FPGA these IP cores go on. So maybe in my fantasy, I can imagine that all these IP cores are on an infinitely large FPGA and they're just connected with one another. So right now, I'm totally agnostic to what my resource constraints are. Then on top of this, I specify a bunch of files here. And so these files you can think of it as a configuration. So it would say that, okay, previously we've mentioned all the IP cores would be on one large FPGA, but in reality, they're not. So when IP cores have to cross an FPGA to FPGA boundary, we would encapsulate packets in this network protocol. And you can actually change the network protocol within them. So this network protocol is on top of Axis Stream. So what happens is you have your Axis Stream that gets encapsulated within a network protocol that you specify in a config. So this could be TCP, UDP, layer 1, layer 2, whatever you want really. And I'll get into those details later on in the presentation. Also, this could also specify the partitioning. Later on in this work, we've actually developed our own partitioner where you don't even need to specify the partitioning. We have for this work, we've implemented a simple greedy partitioner, but a colleague of mine, Mahdi, who's also on this call, so he's working on a more involved partitioner. So if you have questions specifically for the partitioning, he's on the call too. And yeah, so even the partitioning is kind of automated here. So in these files, you just describe the configuration. On top of this, you give a library of streaming kernels. So within our work, we've used HLS, but in theory, it could also be even RTL that abides by the interfaces. So Axis Stream in, Axis Stream out. That gets fed into my tools. And on the output, we have the cluster that you see on the right. And if you see the cluster on the right, you'll see that the library of Axis Stream kernels that we've given to the tools have been partitioned across different FPGAs. And what's not shown is the communication between them is automatically done with IP cores that Galapagos places. Now, just I guess more of a picture, and this is specific to a lot of the stuff. If you guys wanted to implement Galapagos, what you would need is more like a shell like this. So we have a shell that can communicate to the network. We use 100 gigabit. We have a 100 gigabit Axis Stream, which is I think 512 bit wide data, and at 300 megahertz ish works out to be 100 gig, and we have connection with DDR and PCIe. So as long as you have a shell that, for whatever board that you want to support, if you have something like this, then it should work within our environment as well. So just a brief overview on Galapagos. It's a heterogeneous stack, which allows people to connect CPUs and FPGAs together. And the other thing that I didn't show earlier is it also allows us to seamlessly prototype by migrating between CPUs and FPGAs. So at the end of the day, the FPGAs are network connected devices. You also have CPUs that are peers on the same network. And because A, we're using HLS for implementing the kernels, but B, we've also implemented a lot of the routing that wasn't shown in the previous figures. We've implemented the same routing on CPU nodes as well. So you have essentially HLS Axis Stream connected over the network, both in CPU land and in FPGAs. So this opens up the door for iterative development. So you could imagine that you have a large multi-node FPGA cluster. A lot of us work with FPGAs, and we know that FPGAs aren't easy to work with. So we want to maybe iteratively migrate parts of our large cluster that maybe we first implement in CPUs and iteratively move bits and pieces to it on an FPGA. And since at the end of the day, they're communicating over the network, the CPU and FPGAs, the CPUs aren't even aware that they're communicating to FPGAs or CPUs on the other end. They just see an asynchronous network address that they're sending stuff to. So both of these frameworks kind of led to the birth of AIgean. So it's you see HLS4ML creates the IP cores that we want, and Galapagos takes those IP cores, plops it across multiple devices, and stitches them together. The tools combined to deploy neural net on a multi-FPGA fabric. So here's the overall tool flow. There's a lot happening. All of this is automated, but we'll get into a few details bit by bit. So the very left-hand side here, this is probably where your ML expert would sit. So this is where they would have their model, they would train their model, they would figure out what model works for their given application. I figured out that I want this maybe ResNet 50, for example, this modification of ResNet 50. For my given application, it fits my accuracy. I'm done at this point. It then pumps it into HLS4ML, or our modified version of HLS4ML. I'll get into the modifications in just a bit. So, which generates both the IP cores and bridges. So previous to us joining the group, the HLS4ML used to spit out one large IP core for a given network. But what we've decided is, if we want to split it across multiple boards, we would want a smaller granularity. So we've decided that each particular layer of a network would be its own IP core. So instead of a large network, instead of a large IP core, we have a bunch of smaller IP cores for each given layer, on top of which we also generate bridges, which I'll get into in a second right now. So each particular IP core has many dimensions, and with each dimension being a single stream. And at the interfaces, we've decided to wrap it up with a bridge that converts it from a simple HLS4ML stream into a Galapagos stream. And Galapagos stream has a bit more information, such as the routing information that you need to go from one point to another point. Whereas HLS4ML assumes that everything is directly connected. And this is actually an interesting picture if, for example, if you have your own application layer and you want to target Galapagos, for example, you might want to have your own bridge that can translate your own streaming protocol into our Galapagos streaming protocol. So that's something to consider as well. So our HLS4ML layers are then fed into the partitioner, which I've alluded to earlier. For this work, we have a simple greedy partition that tries to fit as many of the layers on one FPGA before moving on to the next. And then all that gets fed into our machine learning to Galapagos layer, which then actually outputs the Galapagos files that is then fed into the Galapagos part of the tool flow that is not shown here. And this can take a couple hours to generate the bit streams. So there are many steps as we've seen, but most of it is abstracted away. And depending on your domain expertise, you may be interested at different levels here. So we can explore this in more like a case study. If I am a data scientist, then all of this would be very overwhelming for me. I would want most of this to be black box. So from a data scientist perspective, I would pump in a model and my output would be a series of bit streams programmed on FPGAs. As a matter of fact, I don't even need to know that they're FPGAs. These are just a network address. I just read and write to a network address, and in the background, it communicates a bunch of FPGAs already programmed. So that's the perspective of a data scientist. It's just a network RPC. However, if I'm an ML IP core designer, so let's say that I want to implement the best version of a conv layer, but I don't want to have to deal with, for example, maybe the other layers of a network. I don't want to have to deal with figuring out how to put this in a much larger system. I just want to implement this one IP core. But after implementing this one IP core, I want to be able to see how it works in a much larger system. Did I make an impact? So this is what the ML IP core designer would see. The ML IP core designer would see the ML models get pumped in through HLS4ML, And there you can actually see that, oh, these are the particular layers. I want to muck around with layer X. And then I would get my HLS synthesizable C++ code and pump the rest into Galapagos, and Galapagos would then, just like before, give us a series of bit streams that are all prepared. So again, at this point, I just worked on the single IP core and not have to worry about the rest of my system. Lastly, and this is maybe, I guess I am a bit biased. This is my favorite part of the, tool flow here, is the data center architecture. So I get a bunch of IP cores. Maybe I'm not an expert in the application domain where these IP cores come from. In this particular set, they're ML IP cores, but they could be anything. They could be any sort of streaming IP cores. And I want to figure out how to partition this across different devices. I want to figure out how they communicate. And I want to optimize that. And I want to be able to say that I've done it for a realistic application. So this is where I would probably do my work, where I get the bunch of IP cores, and then I can even muck around within the Galapagos layers itself. And for that, I'm going to quickly zoom into Galapagos for a quick second here. And we're going to just talk again about what happens at this point. So ML2G, which is the last part of the AIgean Toolflow, generates what the cluster would look like in a series of connected IP cores. So now it's not a general ML description. It's more of, these are the streaming IP cores and this is how they're connected. So, so our last bit before handing off to Galapagos generates that. HLS4ML generates the individual IP cores. We then feed it into the tool flow and it generates our distributed cluster. And if we zoom into one of the FPGAs, it actually looks like this. So our Galapagos middleware generates a couple cores that are responsible for routing, as well as it places the user IP cores, which in this case are machine learning cores, within the FPGA application region. The cores that we generate for routing include one network bridge, and the network bridge's main job is to translate between AXI stream and whatever network protocol that you want. So for what we've developed in-house, one of the co-authors, Clark, has developed a 100 gigabit UDP IP core. So we have a bridge to communicate to 100 gigabit UDP. We also have a bridge to communicate to TCP. We have a bridge to communicate to layer 2 Ethernet. If you have your own network protocol within your network backend, all you would need to do is make a bridge that translates that network protocol into AXI stream. On top of which we have a router. So within the AXI stream protocol, we have an extra side channel that specifies the destination. And this router is aware of the location of every kernel within the cluster and its associated destination. So it knows that, for example, that kernel 1 and kernel 2 are on the same FPGA. So if kernel 1 wants to send something to kernel 2, it would get routed directly on chip, and it would never even see anything off chip. But if kernel 1 wants to send something to kernel 3, which might be another network connected device, it would go through the network bridge, get encapsulated accordingly, and make its way to that particular FPGA. So, and again, reminder that these IP cores responsible for routing are automatically generated by Galapagos. So we're going to get into some brief results just to show that this is this kind of works. So here's a picture of the experiment setup. Our CPUs are Xeon E5 2650s, 24 cores, 2.2 gigahertz, and our FPGAs are FIDA Sidewinders. Here's actually an old picture taken way before the pandemic. So this is our PCIe backplane with a bunch of these FIDA Sidewinder cards. Now it's actually quite full. Hopefully, for my next iteration of this presentation, we'll have an up-to-date picture. Each of these FIDA Sidewinder cards has a ZG19 FPGA, which is about 1 million logic cells. So, and to put in perspective, maybe with the board more people are familiar with, this is about the size of a single SLR region of an Alveo U250. And it uses a 100 gigabit network interface. And to communicate between FPGAs, we have our in-house 100 gigabit UDP core developed by my colleague Clark. So these are just some micro benchmarks before we even put the application down. This is the maximum we'd ever see. So here we have the software to hardware. As you see, throughput is quite low. latency is quite low. And this is mainly because our software driver is not implemented in an ideal fashion. Ideally, we'd want to implement this with something like DPDK that goes below the OS, but for now, we're kind of limited by software. But if we see our hardware, it's running at the line rate, as well as the latency is very minimal. And then lastly, hardware to software cannot keep up for similar reasons that I mentioned earlier when we were looking at software to hardware. So this is the best case scenario if the application itself wasn't adding any overhead. So this is what we can expect. So first, we started with a small neural net. It's a single CPU, single FPGA used in physics applications to calculate energy of a particle. It's about 16K inferences. And my colleagues first did it in SDXL, so not using Galapagos. And they saw about 3 milliseconds back and forth for the 16K inferences. And with the AIgean, we saw 6.3, so it's a little slower. But some more micro results within this, we've seen that the latency of a single inference is about 0.08 milliseconds. And we can do this since we're streaming, which isn't possible via SDXL. But this shows us that the bottleneck here was actually sending the data to the FPGA via the CPU network link. So the takeaway from that is the network link can win it in terms of scalability first, because we can target many more FPGAs. We can stream data, but we should also target a much larger application, an application that would spend more time on an FPGA, or spoiler alert, maybe multiple FPGAs, because our hardware to hardware latency is really good. So the next led to this, maybe this medium-sized application. We have an autoencoder implemented in both SDXL on a single FPGA and AIgean using 3 FPGAs. So a single FPGA, again, we're able to, HLS4ML is able to tune how big the IP cores are. So with a single FPGA, we had to be a lot more conservative with our reuse factor. Whereas with a much larger fabric that we are afforded with Galapagos, as long as the overhead to go from FPGA to FPGA isn't insane, we should see better performance. And that's exactly what we see. We see more than a 3x improvement in performance once we went off chip, which shows that the bottleneck is definitely not within the FPGA to FPGA communication, and which also shows us that we're kind of getting multi-FPGA almost for free here. So the takeaway here is that using a larger fabric allows us to implement larger circuits. And because Galapagos abstracts away the difficulty, we should be able to do even a much larger circuit than this, which leads us to the next big example, which is Resonant 50. This is a multi-FPGA implementation. We actually have 2 different configurations at 660 images per second. We could actually tune it for more, but you might be wondering why we tuned it for 660. That's slightly better than Brainwave, and we wanted to have at least that to say. So we've tuned it for a throughput of 660 images per second, batch 1, 1.9 millisecond latency, if the data is only on the FPGAs. If we have data going from CPU to FPGA at the endpoints, then we have about 7 milliseconds of latency. The 2 different configurations, one uses 12 FPGAs, the other uses 10 FPGAs, and the only difference is DSP utilization within the IP cores. And the reason that is partway through our implementation, we've noticed a much more efficient way to do our DSP utilization, so we switched the IP core. But this also shows how easy it is to swap out your hardware implementation at the very bottom and leave everything else the same. So it was literally just having the tool flow point to a different library of IP cores, and the rest kind of just worked. And we're currently working on more efficient IP cores. So here's a bunch of numbers. There's a lot of numbers going on here, but the takeaway here is at the beginning, we're limited by DSPs. Near the end, we're limited by LUTs. And currently, our partitioner is striving towards an 80% utilization, and it tries to put as much as it can before it hits that 80. So this is where we kind of got this utilization numbers from. So to end, I want to conclude. So here's a summary. In summary, we were able to implement a multi-FPGA CPU neural net framework by leveraging 2 other frameworks, HLS4ML and Galapagos. This gives us tunable IP cores as well as flexible communication due to Galapagos's modular communication. The ML HLS IP cores were deployed onto a cluster of network-connected FPGAs and CPUs, and this communication was abstracted away from the user. So, in conclusion, the creation of larger fabrics with network-connected FPGAs opens a door for more complex algorithms. As we've seen that if we limit it to our single FPGA, we might even get throttled by network performance. But with a large enough fabric, especially because our FPGA to FPGA communication is so cheap, we can create more complex algorithms. And this gives us many opportunities to explore in multi-FPGA ML. And just some acknowledgements. I want to acknowledge my wonderful colleagues. So Galapagos is a huge stack. There's some people working on shells. So Daniel is working on shells. We have Camilla working on connecting SSDs to the network. We have Clark working on really good low-level network protocols, and we have Mohammed working on how to deploy this using something like Kubernetes. So if you guys are interested in any of that, if you contact Paul, Paul can sure make one of them do another presentation. And of course, I want to thank my supervisor, Paul Chow. And these are our sponsors as well. So Xilinx, the National Science Foundation, CMC, and IRIS. And I want to thank all of you. My email's on the slide if you have any questions after, but I'm also welcome to take questions now.